Today we're breaking down Accelerating Scientific Research with Gemini, Case Studies and Common Techniques by David Woodruff and the team at Google Research.
Yep.
The core insight here is this, well, it's documented phase shift. We're seeing large language models, specifically Gemini DeepThink, go from just being passive tools.
Right, like a calculator.
Exactly, to being active research collaborators. And this is in some really heavy fields. And we're talking theoretical computer science, physics, economics.
And the achievements are, they're not trivial. The AI is resolving actual open problems.
Right.
It refuted a conjecture in submodular welfare maximization.
It also found an exact analytic solution for cosmic string spectra, which, surpassed what humans were doing with numerical methods.
And my favorite, it found a fatal flaw in a cryptography preprint about snarks.
Yeah, we'll get to that one. So the whole paper formalizes this kind of playbook for how humans and AI can collaborate, introducing concepts like neuro-symbolic loops.
Where the AI writes code to check its own math.
And vibe proving, which is this great term for scaffolded reasoning, where the human guides the strategy and the AI just crushes the technical details.
It's a remarkable set of case studies.
Yeah.
It really moves beyond the whole AI wrote my email narrative.
Oh, way beyond. This is AI solved an integral that's been bothering physicists for years.
Exactly. And that's the real shift we're digging into today. We're not talking to routine tasks like summarizing a PDF or fixing a syntax error.
No, this is about novel, expert-level discovery.
Right. And to understand how that's even possible, you have to look at the model they were using. This wasn't just your standard off-the-shelf chatbot.
No.
They were using an advanced internal version of Gemini DeepThink. And it had been trained with reinforcement learning, specifically on theorem-proving data.
And it also has that parallel thinking feature, right?
Yes. So instead of just one linear chain of thought, the model explores multiple proof branches at the same time. It's like it's exploring a whole tree of possibilities.
But the paper argues the real secret sauce isn't just the model itself, it's the workflow.
It's the dynamic. They call it the junior collaborator.
I love that analogy. It frames it perfectly. The AI isn't some oracle that just spits out perfect truth.
Not at all. It's more like a brilliant, absolutely tireless, but sometimes hallucinating grad student.
Exactly. It needs guidance. It needs a firm hand.
Which brings us to their core methodology. They call it scaffolded reasoning, or, my favorite, vibe proving.
Vibe proving. So the human researcher sets the high-level strategy, the scaffold.
Yep, the vibe of the proof. And the AI fills in the lemmas, the derivations, all the mathematical grunt work.
And then, crucially, the human has to rigorously verify everything that comes out.
You have to check the work, always.
So let's look at the first big technique where this dynamic just shines, the neuro-symbolic loop.
The case study is from physics, right? Cosmic string spectra.
This was a fascinating example. So researchers were trying to predict these radiation power spectra for Garfinkel-Vacha body strings. And to do that, they needed to solve this one core integral. They call it Whatlog n alpha bladder. And the problem was that the human methods were, well, they weren't great.
They were clunky, computationally expensive. The existing methods involved these really complex recurrence relations or matrix inversions that were just unstable.
So you'd get errors that just blow up.
You'd get catastrophic cancellation issues, yeah.
Yeah.
And the complexity was scaling poorly. We're talking neuronal or into where maybe didn't ask. They needed a better way.
So they gave it to the AI. But they didn't just ask, hey, solve this for us. They used this neurosymbolic process. Can you walk us through that?
So this is where the AI acts more like an agent. It's a loop. Step one. The AI proposes a symbolic math hypothesis, a potential solution.
Oh, sure.
Step two, the AI then writes a Python script to numerically verify that hypothesis against a known baseline.
So wait, it's checking its own work.
It's checking its own work. And step three is the automated feedback. If the code fails, or if the numbers just don't match the baseline.
The error gets fed back in.
The traceback, the error, all of it gets fed right back to the AI. It lets the model prune its own bad ideas without human intervention.
And what was the breakthrough? What did it find?
Well, after exploring this whole tree of possible solutions, the AI discovered an approach using Kagan-Bauer polynomials.
Which turned out to be an exact closed-form analytic solution.
Yes. It went from this messy, unstable numerical approximation to a perfect, exact formula.
That's amazing.
And it was stable. No more catastrophic cancellation. The complexity dropped from oh-no dollars down to own dollars. It was instantaneous.
How? What was the insight?
The AI figured out that the specific weight of these polynomials, this $1 and $2 term, It perfectly canceled out a singular denominator in the integral that was causing all the problems. It was an insight the human researchers just hadn't seen.
That is the absolute dream, right? You struggle with an integral for weeks, and the AI finds the one polynomial that makes it all just collapse.
Yeah, but the paper also shows the flip side. AI not as a creator, but as a critic.
The adversarial reviewer, this is the cryptography case study with the synergies.
Succinct, non-interactive arguments of knowledge. A very big deal in crypto. And there was this preprint claiming a major breakthrough.
Right. So the researchers decided to see if the AI could review it. And they didn't just say, summarize this. They used a really interesting prompting strategy.
Adversarial self-correction.
I thought this prompt was so clever. They told the model, generate a review, then critique your own review for hallucinations, and then refine it again.
They basically told it, be ruthless, but make sure you're right.
And it worked. The AI found a fatal flaw, one that the human reviewers had apparently missed at first.
It found a critical gap between the definition of the cryptographic scheme and the actual construction.
Okay, unpack that for us. What was that gap?
So the definition required what's called perfect consistency. This means that the shadows, which are basically digests of the proof, they have to be identical for every single choice of randomness.
Every single one, no exceptions.
No exceptions. But the construction in the paper only achieved statistical consistency, which means the shadows only matched with high probability.
That sounds like a nitpick. Every choice versus high probability. Why is that fatal?
Because in cryptography, that tiny gap is everything.
Right.
The AI correctly argued that this discrepancy meant an adversary could hunt for a piece of bad randomness and use it to forge arguments. It completely broke the security proof.
Wow. And what about the authors of the original paper?
To their credit, they acknowledged the error and retracted the claim. The AI didn't just find a typo. It found a deep, structural, logical failure that invalidated their main theorem.
That is such a powerful example. The AI is moving beyond just generating text into rigorous critique.
Absolutely.
Now, another area where this paper claims the AI really shines is in something they call cross-pollination.
This is one of the, I think, genuine superpowers of LLMs.
Mm-hmm.
They've ingested this impossibly vast corpus of text, which means they've read all the math textbooks that you haven't.
So they can connect ideas from totally different fields.
Precisely. The MaxCut case study is a great example.
Right. The problem was about bounding the variance of unit vectors, a discrete combinatorics problem.
A classic CS theory problem. But the AI reframed it. It suggested treating it as a continuous energy minimization problem on a sphere.
So it turned a graph problem into a physics and geometry problem.
Exactly. And once it made that conceptual leap, it suggested using the Stone-Weierstrass theorem.
Which is not the tool you'd normally reach for here.
Not at all. It's from geometric functional analysis. It's almost never used in approximation algorithms. But because the AI has read that literature, it saw a connection that a human specialist, stuck in their own field, might completely miss.
And there was another one with Euclidean Steiner trees. The simplex is the best conjecture.
Yes. Here, the AI mapped a graph embedding problem onto a star graph, a simplex. And this is the kicker. It identified this transformation as a one-Lipschitz map.
Okay, I know that term. That basically means it doesn't stretch distances.
Correct. And because it recognized that specific mathematical property, it immediately invoked the Kurzbron extension theorem to guarantee the transformation didn't increase costs.
That's incredible. It's like having a mathematical librarian on call.
That's a perfect way to put it. It's pulling an obscure theorem from topology to solve a computer science problem. It's connecting dots that are light years apart.
Okay, I want to shift to the vibe coding experiment. This was the section with Lance Fortnow.
This is a fun one. And Fortnow is a giant in complexity theory. He decided to try and write a research paper from scratch using an AI-integrated IDE called Anti-Gravity.
Powered by Gemini.
Yeah.
And he called it vibe coding. He went from a blank page to a full paper in about 8 prompts.
And the topic was Search versus Decision for the Complexity Class, 710 Towers. The wild part is, the AI independently discovered the proof that finding an ST2 Padal witness is equivalent to the class text TFP.
Which sounds incredibly impressive, but there was a catch.
There's always a gotcha. The AI tried to include a corollary. In it, it just casually assumed a certain containment was true.
That was actually a massive open problem in the field.
Yes, it just stated it as fact, as if it were obvious.
So it claimed it had solved a famous open problem as just a little aside.
Basically. And this is why that junior collaborator model is so critical. Fortnow saw that and immediately said, whoa, hang on. That's an open problem.
And the AI?
It immediately pivoted. It said, you're right, and corrected the proof to use a reduction instead. No fuss.
So the human expertise was essential. You needed that expert eye to spot the subtle but huge logical leap. The AI did the heavy lifting, but the human was the guardrail.
That's it. It just reinforces that we aren't at the autonomous researcher stage. Not yet. We're at the high-speed amplification stage.
Okay, let's hit on some rapid-fire wins. The paper mentions some specific algorithmic optimization.
Two really cool ones here. First, something called the self-regularized Gumbel sigmoid, or SRGS. It's a machine learning heuristic that people were using because it worked.
But no one really knew why it worked. The classic, it works in practice, but does it work in theory?
And the AI provided the theory. It analyzed the model and the low temperature limit as dollars goes to zero. It derived that the variance term acts as an exact relaxation of the $L constraint.
The $L constraint being sparsity? Right.
Yeah.
Counting the number of non-zero items.
Exactly. And it proved that SRGS induces this cool hybrid regularization. For strong signals, it applies to shrinkage. But for weak noise, it applies a non-convex Dirichlet decompression.
So it explains why the heuristic is so good at keeping the important stuff and just ruthlessly getting rid of the noise.
It found the mathematical justification. The second win was on robust core sets. The AI managed to remove a whole logarithmic factor from an existing bound.
How did it do that?
It questioned a fundamental assumption in the analysis. There was a threshold parameter, $2, and humans had always just treated it as a single global constant. The AI realized, wait a minute, this doesn't need to be global.
It made it dynamic.
It derived a state-dependent threshold, 2 less 2 equal more, and by allowing the threshold to change based on the algorithm's state, it proved a new recurrence relation that improved the approximation ratio to exactly $2 score set.
That is so specific. It's finding these little optimizations in the cracks of the math that humans just glossed over.
It's a result of that parallel thinking we mentioned. It can check the implications of changing one small variable across the entire proof structure way faster than we can.
So we've seen physics breakthroughs, crypto bug hunting, complexity theory. But we have to talk about the limitations. You said it before, the junior collaborator.
Yes, and it's a collaborator with one very distinct personality flaw. Confidence does not equal correctness.
The paper explicitly warns about this confirmation bias.
This is so critical. If you ask the AI to prove a conjecture that happens to be false, it will often just hallucinate a very convincing-looking proof for you. They tested this with the Cortade-Kumar conjecture experiments.
So if you say, prove X is true, it will try its best to please you, even if X is demonstrably false.
You have to use what they call neutral prompting. You have to ask it, prove or refute, give it an out, give it permission to tell you that you're wrong.
And even then, it can still have technical hallucinations.
Oh yeah, it might flip an inequality sign or misuse a constant. You still need that human verifier.
Which brings us to the bigger picture. The paper brings up the potential crisis in peer review.
This is the elephant in the room. If tools like this allow researchers to write valid, high-quality papers 10 times faster,
then the human peer review system, which is already stretched thin, is just going to break.
it'll collapse under the sheer volume. Humans can't keep up. The paper suggests we might need to use AI, like that adversarial reviewer agent we talked about, just to triage and verify the influx of AI-generated proofs.
Fighting fire with fire.
Or maybe using the auditor to check the creator.
And that leads to a really provocative thought to end on. The paper suggests we're moving toward an era of autonomous verification. So if the bottleneck of science shifts from finding proofs to verifying them, does the role of the scientist fundamentally change?
It might. We could just become auditors. But there's an even deeper question, I think. If an AI generates a proof that is correct, but it's so complex that no human can verify it without also using an AI.
Have we actually learned anything?
Or have we just built a machine that knows something we don't, and we have to take it on faith?
That is a thought that will definitely keep me up tonight. We have covered a huge amount of ground here.
It's a brave new world for research, that's for sure.
Indeed it is. Thanks for listening.